Hello and welcome. I am Beth Mashesky, Assistant Research Scientist for Hazardous Waste and Pollutants at the Illinois Sustainable Technology Center, which is part of the Prairie Research Institute at the University of Illinois. As a land-grant institution, the University of Illinois at Urbana-Champaign has a responsibility to acknowledge the historical context in which it exists. In order to remind ourselves and our community, we will begin this event with the following statement. We are currently on the lands of the Peoria, Kaskaskia, Yankashaw, Waya, Miami, Mascoutin, Odawa, Sauk, Muskogee, Kickapoo, Potawatomi, Ojibwe, and Chickasaw nations. It is necessary for us to acknowledge these Native nations and for us to work with them as we move forward as an institution. Over the next 150 years, we will be a vibrant community inclusive of all our differences with Native peoples at the core of our efforts. This webinar and all the Illinois Sustainable Technology Center's webinars are certified green events through the University of Illinois Institute for Sustainability, Energy, and Environment. To find out more about certified green events through U of I, please visit sustainability.illinois.edu. To find out more about the Illinois Sustainable Technology Center's webinars or to sign up for the events email list, please visit istc.illinois.edu/events. A few housekeeping items before we get started. Today's webinar is being recorded. The recording and slides will be available for viewing online in about a week. I'll be sending an email out to everyone who registered for the webinar once those are available. Everyone will remain muted for the entire webinar. You can type in your questions at any time through the Zoom Q&A feature. You will be able to upvote questions that you like within the Zoom Q&A using the thumbs up button under the question. The most popular questions will be asked first, followed by the questions in the order that they were received. If you have technical difficulties, please send me a private chat message. So with that, I'm very pleased to welcome today's speaker, Jim Palardy. Jim is the project director of the Conservation Science Program at Pew Charitable Trusts. He earned his bachelor's in biology and marine science from the University of Pennsylvania and a PhD in ecology and ecology and evolutionary biology from Brown University. In his role at Pew Charitable Trust, Jim identifies emerging issues in science, develops research projects that inform evidence-based policy recommendations, and contributes technical expertise that help ensure the scientific integrity of Pew's environmental programs. So Jim, thank you for joining us, and the webinar is yours.
Thanks, Beth. So as Beth said, my name is Jim Palardy, and I direct the Conservation Science Program at the Pew Charitable Trust. And for those of you who might be unfamiliar with Pew, we are a Philadelphia-based nonprofit whose mission is to improve public policy, inform the public, and invigorate civic life. We work to inform and advocate for evidence-based policy in a wide range of issues, including but certainly not limited to ocean conservation, fisheries management, rural broadband access, modernization of the civil legal system, and antibiotic resistance. The work I'm going to talk to you about today was the result of a 3-year effort that Pew led with our partner Systemic, as well as some other NGOs and research organizations to undertake a comprehensive assessment of different pathways the world could take to reduce plastic pollution. This research led to Pew's 2020 report called Breaking the Plastic Wave, which is available on the Pew website. And of course, the accompanying manuscript in Science, which sort of formed the technical underpinnings for the report. Today, I'm going to present a small set of key findings from the analysis and highlight some things that we can all do to reduce the flow of plastic into the environment. But for more details about the work and a much deeper discussion about solutions across geographies and portions of the value chain, please feel free to, again, download either one of these documents. So as a material, plastic is very useful and even essential to modern life. And this sort of ends up with what I call the plastic quandary. So plastic is cheap, light, versatile, and therefore it's ubiquitous. But the performance characteristics of the material and its low cost is really a double-edged sword, since it's the same properties which make it problematic. Plastic can last for centuries in the environment, choking life on land and at sea. It can release toxic chemicals as the products break down. And of course, it does degrade into smaller and smaller pieces through time. It's literally everywhere in the ocean and on land, from the Marianas Trench up to the summit of Everest. And it's going to be there for a long, long time, simply because it's not worth picking up from an economic point of view. So my talk today is going to sort of center around 5 key questions around the plastic system. First, where are we headed today under a business as usual scenario? Second, given that the business as usual scenario is not a happy future, what is a better way for us to move down? Finally, or not finally, how do we get there? And then in order to get there, what are some of the biggest challenges that remain on the technical and social side of implementing the changes that are needed? And finally, what's the prize? What's the environmental, social, economic prize of achieving a change in the plastic system? So I'll jump right on in, first addressing where we are currently headed in the world of plastic. So although plastic has become virtually ever present in modern life, it's currently projected to continue growing. And on screen are some quick sort of pre-COVID growth projections from the plastic industry. They anticipate a 40% increase in plastic production over the next decade, including more than $400 billion of investment in new refineries in the next year or two. They also anticipate a continuation in the compound annual growth rate for the ethylene market, which was one of the constituent building blocks, if you will, of plastics, of nearly 9%, which is fairly close to historical growth. So essentially, plastic production is going to rapidly increase for the foreseeable future. And in many cases, it's plastics that are the projected endpoint for oil and gas as renewable electricity sources come online. So the growth in plastic usage is strongly linked to the emergence of a global middle class, and that's a category which is rapidly expanding. And this suggests that the industry projections probably aren't wrong, but also that the demand for the services provided by plastic is likely to grow rapidly in the coming decades. The question is then how we get those same services and the same utility out of materials that doesn't come from plastic. So despite the projections for future growth, many parts of the world already look like this. Scenes like this one from Indonesia highlight the fact that solving the plastic pollution problem is not just an environmental problem. It's a human health problem. It's a climate change problem. More than that, it's a moral problem and a question of social justice. And unless we as a society choose to do something about it, it's only going to get worse and worse. So given the magnitude and complexity of the global plastics pollution problem, Pew began to work in 2017 to determine what role we might play in breaking the coming wave of plastic. And what we learned from this initial line of work was fairly grim. The business as usual scenario for plastic pollution is truly horrific. From 2016 to 2040, and in line with industry projections, we estimate that plastic waste generation is likely to double to about 420 million metric tons per year by 2040. At the same time, we estimate that annual plastic leakage into aquatic systems is projected to nearly triple to 29 million metric tons per year by 2040. And the stock of plastics in aquatic systems is likely to quadruple over that same time period to nearly 650 million metric tons. Now, these are pretty astonishing numbers that are pretty hard to comprehend. What does 20 million metric tons of plastic even look like? Well, just to sort of put that in context, 29 million metric tons of plastic annually is about 8 pounds of plastic pollution per foot of shoreline around the world every year. Now, to make your day happier, our work showed that aquatic plastic is only really the tip of the iceberg for plastic pollution. We estimate that nearly 40% of plastic in the municipal solid waste stream ends up in the environment, with the largest component polluting the air due to the open burning of plastic waste, largely in developing economies. But of course, there also is leakage into aquatic and terrestrial habitats globally. And another important consideration is that the plastics value chain from production through use and disposal releases an enormous amount of greenhouse gases. And if plastic use continues to grow at historical rates of about 8% per year, as I said earlier, the greenhouse gases released from the production, use, and disposal of plastic all by itself would account for nearly 15 or 20% of the global carbon emissions budget allowable under the Paris Agreement in 2040. So given the sort of gruesome nature of the business as usual case, what's a better way forward? How do we deal with the plastic pollution crisis? And when we started our research, there were really four main competing ideas. First, ban it. Just get rid of as much plastic as possible, stop making excuses, and just break free from plastic. The second idea was to essentially burn or bury it. Essentially collect all the waste and the waste plastics that are produced on a global scale, and then either landfill or incinerate it, because landfills are cheap and plastic waste, according to some people, is a relatively low carbon fuel. You can also try to clean it up and focus on restoring ecosystems and removing plastic out of the environment. Another common idea that we hear from the plastics industry is that we should be able to recycle our way out of the problem. Essentially, that if we collect as much plastic waste as we can and recycle everything using both traditional and advanced recycling methods, also known as chemical recycling, that we can monetize low-value feedstock and really promote recycling as the solution to the global problem. So despite these competing ideas, some of which have very loud lobbying voices here in Washington, D.C., there was little fact base to answer several important questions that really require answers to decide which pathway is the right one. So how do each of these strategies perform on environmental, economic, and social metrics? How applicable are each of them to different types of plastics, different materials, and different geographies? What levels of investment are required in order to solve plastic pollution using these different ideas? How quickly can they be implemented? And then, of course, how do they interact with each other? Because the plastics value chain is a fairly complex system. So to try to make sense of these competing ideas and to create a path forward, Pew engaged a large team of 17 global experts from academic, applied, industry, and from investment houses. So they brought a very vast knowledge across the plastic value chain and from around the world. And these experts supplemented a core team of about 30 between Pew and Systemic. And the goal for the expert panel and for the project as a whole was to provide a robust and evidence-driven analysis to policymakers, industry leaders, investors, and other key stakeholders, which highlights the economic, environmental, and social implications of different pathways towards stopping plastic pollution. And the result of our work was the Plastics to Ocean, or P2O model. P2O is a data-driven coupled ordinary differential equation, or ODE model, which can estimate the effects of desirable and undesirable changes in the plastic system. The model estimates uncertainty in the size of stocks and flows through use of a Monte Carlo sampling approach. P2O is currently able to track and respond to changes in plastic mass flows, per ton costs, employment opportunities, and greenhouse gas emissions associated with each step of the plastic value chain. And on screen, I've got a simplified computational map for plastic in version 1 of the model. The boxes on screen represent key steps in the life cycle of plastic, sort of starting in the upper left here with demand for the material properties and utility provided by plastic through production and use phases, disposal, collection, sorting, and into recycling, safe disposal, and then mismanaged waste that is either deposited into open dump sites or results in aquatic pollution, terrestrial pollution, or an open burning, which is essentially air pollution. And of course, the arrows represent flows between and among the boxes. So ultimately, P2O allows us to track and respond to changes in plastic mass flows, costs, employment, and greenhouse gas emissions through the plastic value chain. And then as a result, estimate how interventions and policy actions in the system can change the magnitude of these flows. But before we can run the model as we built it, we had to sort of put some numbers into the basic system. And since waste collection systems vary vastly by geography, as do the relevant economics of waste management, we had to figure out how to parameterize this in an appropriate way. And so we constructed 8 geographic archetypes that were based on population density and per capita income based on the World Bank income categories. And the idea was that these geographic archetypes would reflect differences in both the economics, but also the sort of the social side of waste management systems. The other thing that we had to do was consider how plastic types themselves differ in their pathway through the value chain. And the material properties of different types of plastics makes them behave differently, not only in supply chains, but also once they get into the environment. And getting these behaviors right was key to producing a defensible and usable model. And so we modeled 7 different types of plastics, beginning with rigid monomaterial plastics. So this would be things like drink bottles or yogurt containers and things like that. We modeled flexible monomaterial plastics. This would be things like Ziploc bags and produce bags you get at the grocery store. We also modeled multi-layer or multi-material packaging, commonly called sachets. So this would be things like chip bags or single-serving ketchup packages you might get at a fast food outlet. These have different layers of plastic that are sandwiched together, and frequently they also have an aluminum foil liner on the inside. We also modeled 4 types of microplastics, primary microplastics: tire particles, textile microfibers, plastic pellets, and personal care products. And then we collected data to model each of these 7 types of plastics through each of the geographic archetypes. Within geographic archetype and plastic type, we identified appropriate interventions in the plastic system that reduce plastic pollution, or at least would be hypothesized to reduce plastic pollution. Now I've got a selection of potential interventions here on screen. And of course, it would be normal for these interventions, because they can and regularly do interact with each other, to change rates of plastic mass flowing through our model. Now, in terms of priority, the interventions were applied using what's known as the waste hierarchy, starting from reducing plastic quantities in the system. So this would be things like just eliminating unnecessary plastic, moving to reuse models or new delivery models, and then moving down into plastic substitutions. So this would be things like taking plastic out of the system and replacing it with paper, coated paper, or compostable plastics, or other compostable materials that would take the place of plastic in packaging or other applications. What can't be reduced or substituted would then be recycled. And recycling rates would be increased through 4 major processes. First is designing for recycling. That's essentially just redesigning products so that they can be recycled more easily and profitably. Expanding waste collection, because if you don't pick up the plastics, you don't have the raw materials for recycling. And then, of course, scaling up both more traditional mechanical recycling methods as well as more modern or advanced chemical recycling approaches. And then what you can't reduce, substitute, or recycle, you can dispose of responsibly. And in our model for some of the scenarios, we assumed that we would develop new both sanitary landfills and waste to energy or incineration facilities to safely dispose of plastic. And also, in order to make sure that we weren't offshoring our problems, we reduced plastic exports to high leakage regions. Now, plastic that can't be dealt with under any of these interventions would remain mismanaged in the model. So now, for each of those interventions, we had to estimate what the maximum potential was for scaling up these solutions across a wide suite of product categories. And so I've just got a few of these product categories on screen. And so we had to assume this for approaches currently implemented live in the world, as well as for known technologies that are proven in the lab, have some prototypes out there, but are maybe not yet sort of fully integrated into the market. And so, for example, one sort of test that we did to estimate maximum feasible change for new technologies, which might reduce plastic from the system, and that's sort of the dark blue portion of these products at least, was to go through a 4-part test. We asked if the technology for removing plastic from the system was ready. We asked a performance question of whether or not the intervention or substitute material satisfied performance and health requirements of the plastic use it replaces. We asked whether or not the intervention was affordable. and of course, affordable in different contexts, right? A fairly inexpensive solution in the United States might not be economically feasible in rural India, for example. And then we asked, again, a culturally relevant convenience test of whether or not folks thought, the experts thought that there would be approval in the marketplace for these alternative products with respect to lifestyle and convenience. And so based on answers to these questions and a scoring criteria we developed, interventions were scaled through time in the model. We then, of course, had to put these interventions together into scenarios that we would model. And on screen, I've got a summary of the interventions that I just sort of talked through a couple of slides ago on the vertical axis there, and how they were implemented into 6 different scenarios across the columns here. In this slide, gray check marks essentially reflect commitments that have been made by corporations and governments, and black check marks represent interventions that are scaled up at maximum feasible rates that I just described. So we modeled 2 baseline scenarios. First, a business as usual case, where current plastic and waste management industry projections are simply followed through to 2040. We have a current commitment scenario where all of the corporate and government commitments to reducing plastic pollution that we were able to identify by the summer of 2019 were implemented beginning in 2020. And then we focused on sort of the future policy change scenarios. We modeled 2 downstream scenarios focusing on collect and dispose. And this is sort of roughly equivalent to the burn and bury idea I introduced earlier. We introduced a recycling approach. And then we modeled an upstream scenario, which focused on reducing and substituting plastic from the system, which is somewhat akin to the ban approach. And finally, we modeled a system change scenario where we essentially pulled all the intervention levers as hard as we could to the maximum feasible extent to see what would happen. And here's what we found. What we found when we pulled all the intervention levers was there was no silver bullet to stopping plastic pollution, that essentially the 4 competing ideas, none of them was right. They had to come together. But there is hope. So first, and as I mentioned before, the business as usual projection is really grim, with aquatic leakage growing nearly 3-fold between 2016 and 2040, up to about 29 million metric tons annually. The scenario where we modeled current commitments, however, isn't a whole lot better. It only shows a 7% decrease in annual aquatic leakage in 2040, which still represents more than a 100% increase from current levels of leakage. So obviously we're not doing enough, and we need to scale our level of ambition. Now, interestingly, we found that the single lever upstream and downstream scenarios performed pretty similarly. And I'm not showing uncertainty bounds in this slide, but you'll just have to take my word for it that their uncertainty bands have a lot of overlap throughout the time series, and especially in 2040. So although each of these scenarios took a good chunk out of aquatic leakage, they don't really result in annual leakage rates below what they were in 2016. And it's essentially sort of a continuation in a sort of a flat space. And they barely get back to leakage rates from 2020 by 2040. So it's really only the system change scenario that looks really promising. And the system change scenario represents an 82% reduction in aquatic plastic leakage in 2040 relative to the business as usual case. Importantly, it also represents about a 50% decrease from current leakage rates. And this honestly is pretty good news. It says that in the next 2 decades, we can make a massive impact on plastic pollution by scaling up programs and technologies that are currently available and ready to implement. So how do we get there? This is what the system change scenario looks like. The colored areas represent how plastic demand is addressed through various policy interventions and the ultimate end of life locations for each unit of plastic utility. So broadly speaking, by 2040, nearly half the plastic in the system is removed, about 30% through plastic reduction strategies, and then another 17% through substitution strategies. An additional 20% of the plastic in the system in 2040 is recycled, 23% disposed of in modern and controlled manners. So although you can see that the quantity and proportion of mismanaged plastic waste, that's the red bars down here, is greatly reduced over time, it's certainly not eliminated. And by 2040, even under a system change scenario, more than 40 million metric tons of plastic enters the environment on an annual basis. So this reflects a need for future innovation and investment to truly solve the plastic pollution problem. One thing I will note about this slide that I've always sort of found fascinating and why this problem is so difficult, and really highlights the need for a system change, is sort of this very, very light bar here at the bottom, the first slice or the first wedge. And that's the aquatic plastic pollution slice. So it's really quite a small proportion of overall plastic production. And it's the fact that we need to solve for these slim slices at the bottom out of a much larger sort of universe of plastic that makes the problem really, really hard and really in need of a system level change. So moving on, how do we get to the system change scenario? What needs to happen on a global scale? Well, the first thing we need to do is think about the 130 million metric tons of plastic that we can remove from the plastic system annually by 2040. And the place to start is just obvious, right? We can remove unnecessary plastic from the system. For example, Coke cans don't need to be wrapped in a plastic container and then wrapped in plastic. It's simply unnecessary plastic in the system. We figure we can get rid of about 34 million tons of plastic on an annual basis simply by pulling this unnecessary plastic out. So major opportunities for removing plastic also come from the development of new business models for the delivery of the utility that's provided by single-use plastics. This might mean, sort of bringing back the metaphorical milkman, using some sort of refillable container solution for some products. This requires the development of take-back services and reverse logistics, concentrated product distribution systems, and there's many of them coming to market right now, like the cleaning products that are offered by Blueland. And there's others, and then they round out this category. And finally, we considered consumer reuse models where single-use products and packages are replaced by reusable versions. So this would include things like reusable water bottles and grocery bags, but also some commercial products like reusable cutlery and crockery in places like restaurants and cafeterias that currently use single-use disposable plastics. So what can we do as individuals? As I said earlier, the best thing to do to help reduce plastic pollution is simply to use less plastic. And some simple examples of how we can do this in our daily life, right? We can use reusable plastic containers or glass containers instead of plastic to store our lunch and leftovers. We can carry reusable water bottles instead of purchasing or using bottled water. Moving on, I guess, to more exotic or seemingly exotic things, we can start to use refill models. It's currently available for cleaning products, some groceries, dog food, and an increasing number of products as time goes on. Some of these refill models, like Loop, which I've got on screen, which is the grocery service which delivers all of its products in fully reusable containers, are truly new to the marketplace. But other refill models, things like bulk purchasing in grocery stores, have been around for a while. But they both remove plastic from your kitchen. The other thing that we can all do, especially in the wealthy West, is drive less. It turns out that car tires are one of the largest emitters of plastic pollution in wealthy countries that we were able to model. So another way to reduce plastic pollution from a source that doesn't have a solution at this point, and that's tire dust, is to simply drive less and instead walk, bike, take the bus, or train more. Next, we can replace plastic with other materials that serve similar functions. In many cases, manufacturers can return to using paper-based materials like they did for decades before they started incorporating plastic. Paper by itself and various types of coated papers and cardboards can replace more than 30 million metric tons of plastic per year by 2040. And we also estimate there's an additional nearly 40 million metric tons of plastic which can be replaced by compostable plastic materials, such as those offered by companies like Notpla, which is pictured here. So finding substitutes for single-use plastics in our own lives is becoming easier every month. In some spaces, substitution really is as simple as choosing from long-standing alternatives. For example, you can choose to purchase clothing derived from natural fibers, like cotton, wool, linen, or silk, instead of products that are derived from polyester or other plastic-derived synthetics. In the kitchen, things like wax-impregnated cloth can serve as a substitute for plastic wrap, and there's more and more resealable things like silicone pouches, which can be substituted for Ziploc bags. Another thing we've all seen, I'm sure, when ordering online is that some larger retailers now provide packaging that's designed specifically for their online systems. It does get rid of many of the design elements used for retail packaging, which is why it's only the large retailers moving here. But choosing these options, for example, Amazon does frustration-free packaging, typically shifts packaging from plastic to cardboard, and also makes it easier to open. The third lever to pull that we think can really scale well is the fact there's a lot of scope for growth in the recycling industry to the tune of about 84 million metric tons per year by 2040. In order to do this, we need to increase the number of products that can be profitably recycled. So for example, the green dyes in Sprite bottles, for example, lower the resale value of the entire batch of recycling that they can be a part of. So simply removing the green dye and other types of additives like dyes from easily recyclable products adds value to the recycled product. And by doing this and other types of approaches known as design for recycling, we think that the proportion of profitably recyclable plastics can increase to about 54% globally, up from about 20%. Second, we estimate that system change will create a 2.5-fold growth in the demand for recyclate. This would have to be scaled to meet relevant government regulations or corporate commitments, such as recycled content standards. And of course, a lot of these things will be driven by increased consumer demand. In our own lives, what can we do? Well, the easiest thing to do, for now at least, is to recycle properly. It's not the easiest thing to do by any stretch of the imagination, but it really is important if recycling is going to be made economically viable. So make sure you follow the instructions. And what's starting to happen more and more is that many products contain a set of instructions that looks like this on the exterior packaging. And it's important to really take a look, because sometimes there's actually multiple different types of plastics that are wrapped or almost shrunk wrap into each other. And it's important that you don't contaminate the batch by recycling the wrong things. So this label tells you how to prepare the packaging. So for the plastic tray, you're supposed to rinse it. Tells you the likely availability of recycling in your location. You can probably recycle a paper box. You probably can't recycle the plastic wrap, but you can maybe recycle the plastic tray. And finally, the instructions sort of tell you what component of the product is part of each column here. So the box, the wrap, and the tray. So unfortunately, you're not really done just by looking at this, because of this asterisk of check locally. For this plastic tray, you really do have to look online and find the recycling number and know what the numbers are in your local community. And it's important that everybody does this, because throwing other recyclables or also overly contaminated recyclables into recycling bins, which is known as aspirational recycling or wish cycling, will pollute the entire batch and might result in the entire load going into a landfill. Finally, there's a lot that needs to be done globally to properly dispose of the plastic waste, which can't be reduced, substituted, or recycled. And we think that excess capacity of about 100 million tons of controlled disposal, or almost 23% of municipal solid waste plastic, will need to be dealt with additional investment in safe disposal facilities by 2040. And this type of solution needs to occur in engineered sanitary landfills, which prevent chemicals from leaching into the environment when disposed, or through modern waste to energy incineration facilities, which produce electricity, industrial heat, and of course, importantly, have modern emissions controls. The other thing that we can all do is export less waste and deal with the problem we've developed locally. The most important thing potentially for all of us as citizens is to simply get involved in pushing for governments and corporations to act. Governments at all levels play a key role in setting the policy framework for social and environmental protection, for legal accountability, and for incentivizing innovation and investment. Some potential examples can be setting targets for recycled content or taxing virgin plastic, thereby changing the economics of recycling and making recycled plastic more valuable, and decentivizing the production of virgin plastic. Governments can set supply chain standards to minimize additives and colorants, fund consumer education, de-risk innovation in the plastic space by funding institutional R&D or creating blended finance mechanisms to lower capital costs. So it's really important that this becomes an issue politically, that you push it in elections and follow up with your representative to support bills and policies that begin to address plastic pollution. Another route for involvement is to ask your employers about how they include plastics in their own sustainability reporting mechanisms, and then to push for transparency and accountability in your own office. Take a look at sustainability reports for companies you invest in or your employer and see if there's anything in there about plastic. And if not, ask why not and what they're going to do about it. We have some good news actually to share in this space over the past few weeks. As I've presented, there is a clear path to achieving the system change scenario. Governments and corporations are beginning to show action in the plastic space, banning single-use plastics in many places around the world, implementing extended producer responsibility schemes, and also using various modeling approaches to develop locally relevant evidence-based policy. And in the very recent history, just in March, actually, in the past couple of weeks, there's some also good news at a global scale. So early in the month, at the 5th session of the UN Environment Assembly, a commitment was made by countries to develop a legally binding agreement to end plastic pollution. The resolution addressed the full life cycle of plastic from production all the way through to disposal. And the goal is for a treaty about plastic to be developed over the next few years. Now, of course, political pressure from all of us is going to be necessary to make this treaty useful, right? It's extremely likely that various stakeholders, plastic industry and others will push hard to ensure that the treaty reflects their own views and desires. So there will certainly be more to be done in this space, and hopefully more news in the relatively near future. So attaining the system change is ambitious, but I hope I've been able to convince you that it's doable. That's not to say there aren't challenges. In the next few minutes, I'm going to talk to you a little bit about what the biggest challenges are. Let's take a look. So the first thing I think that we all need to keep in mind, especially when we're thinking about necessary R&D in order to solve plastic pollution, is that we have to think about meeting people where they are. I love learning about all the fabulous primary research that's coming out of research universities. But from an applied perspective, it's not always the most useful, because this up on screen is what sorting for recycling looks like in some of the world. And this is what recycling looks like. It's essentially a couple of people in a garage. This is what industrial composting looks like in many places. And of course, this is how much of the Western world recycles by compressing it into bales, putting it in ships, and sending it overseas. So when we think about designing applied research for impact, we need to keep a few things in mind. First, that low tech and low investment solutions are really what's needed to solve the plastic problem at a global scale. Second, that infrastructure needed to make things like advanced recycling or advanced composting methods just doesn't really exist in much of the world. And third, that it's these hyper-local contexts that will really drive differences in determining what materials are theoretically recyclable versus what is actually recycled. And therefore, that will determine what materials can be part of a circular economy. The other thing we need to focus on is reducing costs. We have to bring costs down for recycling and substitution, because they simply won't happen at scale if they're not affordable. So what I've got up on screen here is a global cost curve for plastics in 2040, assuming implementation of the system change and all the changes that it entails, and ignoring the externalities of plastic production, which would include, of course, carbon pollution. So for this figure, the height of the bar represents the total value chain costs per ton of dealing with plastic from production through end of life. And the width reflects the mass of plastic utility being replaced. So as you can see, reducing plastic from the system is a win-win. That is, the costs are negative. This has to do in most part from the fact that producing plastic, beginning from drilling through oil all the way through manufacturing, is pretty expensive. Moving to the right, you can see that following implementation of design for recycling, a lot of recycling is profitable in 2040, but not all of it. You can see a couple of bars here that actually represent recycling in high-income countries, which is going to occur at a net loss after accounting for the costs of collection and sorting. And this is really a finding that calls for innovation in the recycling and material science space. And probably the most glaring thing here that you can see is that existing substitutes are currently quite expensive after accounting for collection and safe disposal methods for them. So there's a few things that I take away from the cost curve and thinking about research needs on costs. The first is that solution uptake is really driven by direct financial costs in much of the world rather than integrated social costs. So bringing cash out of pocket costs down, especially in the recycling and substitution wedges, is necessary to solving plastic pollution at a global scale. Second, a lot of products are likely to require financial support to transition through the valley of death from the lab into the market. And so governments and industry need to be ready to fund that work. And third, for many policy solutions to price plastic appropriately, the social cost of plastic rather than the financial cost of plastic. So this would include things like carbon emissions or cleanup, and the cost of environmental degradation really needs to be included in the financial cost of plastic. Another challenge that's really a tough one and something that really needs to happen is the need to scale up collection at a global scale. And it truly is a massive problem. More than 500,000 people need to be connected to collection services on a daily basis from now through 2040 to close the global waste collection gap. And the funds needed to invest in the equipment and processes to do this are unlikely to become available from taxation in low and middle income countries over the next 2 decades. So funding collection remains a major gap that requires policy innovation, perhaps through things like extended producer responsibility policies or a virgin plastic tax or other mechanisms. So one chart that I got on this slide that highlights the need to scale collection and innovation in collection shows the sources for aquatic plastic pollution by geography, with urban sources on the left, broken into the different income categories, and rural sources on the right. Now, what you'll see is that a really high proportion of aquatic plastic pollution comes from rural locations, where collection is really pretty rare on a global scale, and it's also very expensive, partially because the density of waste and plastic density in particular to try to get some value from collection is relatively low. So it's this fact and the complexities of doing waste collection in rural scenarios is likely to limit the ability to scale recycling solutions in many geographic locations, and it really calls for innovation. The second chart I've got up here shows that at a global scale, at least, more than half of the plastic collected for recycling is collected by workers in the informal sector. So these are folks that are often known as waste pickers. And this indicates that there's a value in waste at a global scale. And then also, of course, the value in plastic is mainly thrown away when we use sort of a Western approach to formalize waste collection. So a couple thoughts here about scaling. First, at a global scale, waste is truly collected for its value. And accordingly, removing the value from the plastic waste stream, such as by lightweighting plastic or making it thinner, is really unlikely to reduce plastic pollution, but instead could actually make it worse because it disincentivizes collection and recycling. Second, local empowerment is absolutely essential. And one has to work with locals to understand their needs, desires, and of course, their relevant social context. For example, most waste pickers view themselves as entrepreneurs. And so the social consequences of removing them from dump sites has to be taken into account. And third, to solve the global plastic pollution problem, we really have to develop solutions that work at low plastic densities. One way to deal with some of the challenges that I've already discussed is to figure out how to solve flexible plastics. So on screen, I've got a figure dissecting the production, collection, and leakage of macroplastics by plastic category for rigid monomaterials in dark blue, flexible monomaterials in light blue, and then multi-layer plastics in red. As you can see, rigid plastics account for about 40% of production, but only about 20% of pollution. And of course, it's the flexibles then that make up a slight majority of production, but the vast majority of pollution into the ocean and on land. And this is because flexibles have almost no collection value. So to solve flexibles, we need to minimize multi-layer packaging. It's really hard to recycle multi-layer packaging, almost impossible, in fact, without advanced recycling. So we need to reduce the quantity of flexible monomaterials while simultaneously increasing their value so that we can incentivize collection. And this, of course, is another strike against lightweighting. And we have to figure out microplastics. They honestly remain a major challenge even under the system change scenario. In fact, they're likely to increase in quantity through 2040, regardless of the application of the system change scenario, simply because of projected driving rates in high-income countries. So that's why in the 4 types of microplastics that we modeled, tire dust accounted for nearly 80% of the primary microplastics produced. So although solutions to tire dust remain largely elusive, there are cost-effective solutions to plastic pellet pollution, textile pollution, and personal care product pollution. And these solutions are typically at the source of production, commonly in manufacturing facilities, actually. For example, to solve textile microfiber pollution, you can solve a good chunk of the issue simply by having manufacturers wash synthetic fibers several times at the factory before cutting, finishing, and shipping them out to end-use consumers. I'll also really highlight that we were unable to model many sources of microplastics because of the lack of information that was available in 2018, 2019. Of particular importance, actually, more data has emerged over the past few years about the importance of paint. It's really important because paints contain about 40% plastic content on a global scale. And some preliminary estimates that we're working up suggest that paint could actually be a larger source of primary microplastics than tires. And just like tires, collecting paint microplastics from paint flaking off homes and ships and whatnot is going to be an absolutely gargantuan task. So what's the prize? What's the prize if we can implement a system change scenario? Why should we really be thinking about implementing it and doing the research and working the politics to make it happen? Well, quite simply, achieving a system change results in a better future for the environment, for the economy, and for local communities. For the environment, moving towards a system change will result in 24 million metric tons less aquatic plastic pollution on an annual basis and 25% fewer greenhouse gas emissions in 2040. For the economy as a whole, system change results in lower cost to government to the tune of about 70 billion in net present value, as well a decrease in private costs to the tune of about $1.3 trillion by 2040. And for communities, system change results in more jobs. Many of the new business models for delivering plastic utility are actually fairly labor intensive. And so we estimate that there's about 700,000 more jobs that would exist in the plastic value chain under the system change scenario than under the business as usual case. Or maybe it's just simple to think about a picture like this, where kids are able to play safely on the beach, regardless of where they happen to live. So with that, I will be happy to take any questions that you might have.
Thanks for a really interesting presentation. We do have a number of questions already.
So Beth, I don't know if others can hear you, but I can't.
Can you hear me now? Looks like everyone else can hear me. Jim can't hear me.
So
okay.
Given that, while I wait for you, Beth, maybe I'll just start to work my way through the question list. Does that make sense?
Yeah.
Yes? Okay. All right. So the first question that I see is one that was asked almost up front. It says, why is aquatic plastic pollution increasing faster than plastic generation in general? Well, with aquatic pollution increasing 3 times through 2040, while plastic generation is only increasing at 2 times. Well, what this really has to do with is the fact that in the developed, wealthy world, we have effective waste collection systems in place already. And so it's relatively easy for us to scale up effective collection and disposal in the West because the systems are in place. It's different in the developing world because they don't have the tax base in order to essentially build new systems from the ground up and then fund the ongoing costs and maintenance of those systems. It's very, very likely that the middle class in those countries is going to grow faster than the tax base and the ability to build a lot of these components in. And so it's for that reason, it's really the development of a global middle class in the context of more plastic in the marketplace in general, which results in more plastic pollution when compared to just plastic production in general. I don't know, Beth, you want to see if you can work now?
Can you hear me?
No.
Check the chat.
Okay, I will move on to the next question then, unless you can figure out a way to do this in the meantime, unless something's in chat. Oh, the audience can hear you. My audio is way up. So I clearly have a technical issue on my end. How do you want to do this? Do you want to just tell me which ones to answer in the chat while I try to figure out what's going on my side?
Sure, I'm typing to Jim to continue answering the questions.
Okay, continuing to answer questions with upvotes first. All right. Upvotes, there's one. So the question is from Tessa Murray. How can we ensure compostable packaging does not develop its own unintended consequences, like the proliferation of PFAS chemicals that has been used in compostable package linings? How can we ensure that? Well, ultimately that comes down to regulation, right? And this is probably going to be some combination of figuring out what works in other regulatory environments, perhaps in the EU or in Canada, where there is more of a protective regulatory system in place rather than in the US, where the burden of showing impact is flipped. So I don't know that there's a really good answer there, honestly. I think it's just going to be up to us and to research scientists and NGOs and folks like the EPA to really keep our mind on this and track things as it goes forward. Okay, another question that's been upvoted is, why is it that even for the best case scenario, the number is still high at 8 million tons per year? Is it because of the increase in demand? Well, in a way, yeah. This again comes back to the development of a global middle class. And as people get wealthier, they expect to live more Western type lifestyles, which do include a lot more plastic. So that's the first part of the answer. The second part of the answer is people are still going to pollute. You know, there will always be things like just throwing plastic out, littering. There will always be components of microplastics that are just going to be impossible to reduce. For example, you know, tires currently, right? As you drive along the highway, along the interstate, the friction from the tire against the road surface creates microfibers of tire dust. And how can we possibly deal with that. There are some interesting ideas out there, essentially putting like little boots sort of behind the tire to try to suction up some of the microplastics that are produced, but it's not going to capture everything. And unless you want to build, at the cost of trillions of dollars globally, probably more than trillions of dollars, stormwater collection systems across every mile of road, there's always going to be issues like that as well. Part of it too is simply it's just not possible to scale up some of the solutions fast enough. And as I said, a big component of that is waste collection services. To incorporate 500,000 people into waste collection services on a daily basis between now and 2040 is truly a monumental task, especially in places that don't have the investment dollars needed to buy collection vehicles and build sanitary landfills on the timeline that is needed. That is one of the biggest problems, and collection services are going to be key for many of the solutions that can be implemented downstream, whether it be effective disposal or recycling. And so there's some bottlenecks in the system like that that are simply bottlenecks, and there is going to have to be innovation in the space to get from that remaining sort of 8 or 9 million tons per year of pollution down to zero or as close to zero as we can get. Okay, looking for upvotes. Okay. A comment that we live in a rural area and drive our recyclables 25 miles round trip to town, or pardon, 25 miles one way to town, but still can't find a place to recycle glass. So emphasize the need for rural collection since few people there recycle. So that's absolutely the case, and that's the case here in the United States. And so you can imagine in developing economies that where waste collection is much less common, that rural collection is a bigger challenge. And what ends up happening in many developing economies, rather than just throwing it out into typically fairly well managed sanitary landfills, even in rural areas in the United States, they simply burn their waste in their backyard, which transfers all the pollutants in the plastics into the air, and then of course results in a fairly heavy toxic burden on folks in those areas, which of course results in all kinds of health issues. So developing collection services in the rural low-income areas is absolutely one of the interventions that's needed to scale up rapidly, that we identify pretty strongly in the Breaking the Plastic Wave report. Okay. So the chart shows the bulk of aquatic plastic pollution coming from upper and lower middle income countries. Is that plastic that was actually used in those countries, or wealthy plastic nations shipping the plastic there, or both? Well, so that's a good question. So that figure, let me try to pull it back up here. Here it is. Right, so it's the light sort of middle two colors for pollution coming from lower middle and upper middle income countries, both in rural and urban settings. So that's largely plastic that's used in those countries. What we were able to do, luckily, in Breaking the Plastic Wave, was remove China from the import-export numbers that are in the United Nations Comtrade database, which was the primary source for tracking plastic import-exports, simply because China prohibited the import of waste plastics a couple of years ago, and they were by far the largest importing country for plastics. So when we pulled China out, this is actually what remained actually used in these lower and upper middle income countries. And again, a large part of the high numbers here because there's very, very large populations. So countries like China are in these middle income categories. But as well, they don't have the well-established waste management systems that can manage large quantities of plastics. And so it really is the domestic plastic, in the most part, which is resulting in this high quantity of leakage from these middle income countries. Okay, a good question. What's my impression regarding the role of chemical recycling in the future? Phys.org recently released a report yesterday citing the issues with chemical recycling and the minimal value relative to the environment. So chemical recycling was actually one of the more contentious issues that we had when we were developing the report. It's got some really, really big backers. And honestly, a lot of the primary research coming out of universities is sort of in this chemical recycling or advanced recycling space. When we really dove into the data, we honestly didn't see a strong likelihood for chemical recycling coming online in massive quantities by 2040 for a few reasons. First, it really honestly still is in almost a demonstration stage. Second, a lot of the facilities that are operating have a hard time getting the feedstock that they need. And because a lot of these facilities are sort of still in the early stages of operation, some of their outputs produce not the highest quality outputs, and so most of the outputs from chemical recycling are turned into they're burned. So it's not actually recycling. It's not plastic to plastic. It's just taking the typically fairly low value plastics, which is a good thing, but then turning it into fuel that's either burnt in vehicles or in incineration facilities, typically as to produce electricity and heat. So we don't see a huge role for chemical recycling unless the economics change and there's some more wins, honestly, that start to happen in that space. The other thing that's really relevant about chemical recycling is that after you incorporate all of the greenhouse gases associated with collection, depolymerization, and then remanufacturing, they release a lot of greenhouse gases. And so from a climate change perspective, they're really not a solution at all to the plastic pollution problem. So many of the answers to plastic pollution seem to require the increased use of paper, which kills trees we need for oxygen, and also water for rinsing, which will then foul our water. So won't solving the plastic problem just rob Peter to pay Paul, as making problems with decreased trees and clean water? So on the margin, it's certainly a possibility. The answer to the other extent, though, is that the quantities of paper that we're talking about are really not particularly large on a global scale, have been produced in the past, and could certainly be produced with more recycled paper in the future. This was another one of those things that we really tried to dive into the details to get it right, to make sure that the likely locations for additional forestry products wouldn't be in places that are already heavily logged. And what we found was that there is actually capacity to sustainably manage forests to produce the necessary paper products to replace plastics. Yeah, so I think I'll just leave that one there. Another question: does it help for communities to charge customers to use plastic bags? Our former community tried this and reduced plastic bag use until COVID hit. So this is actually a really interesting area of research, charging people for plastic bags. Certainly on the margins, there are fewer plastic bags produced and used. That said, there's some really interesting research that's been published that showed that if you started charging people to use carrier bags from the grocery store or banned them from the grocery store, what they saw was an increase in sales of the smaller sizes of garbage bags. And so it seems that many of the carrier bags that people were using from grocery stores, at least in the West, the studies I'm thinking of are from California, actually, resulted in more or less the same number of plastic bags being used, because it seemed like a lot of people were reusing their plastic grocery bags as liners for their waste bins under their desk. Now, there's obviously solutions to that. You don't have to have a small lined bin in many places, but it's an interesting question about incentives and unintended consequences, and it's because the mass of plastic bags isn't absolutely massive. They do blow around a lot, and so they are a problematic plastic. But that really does highlight the need to think very carefully about implementing solutions so that you don't end up with really unintended consequences and or incentivizing other things that you just don't foresee. So that's another really good question. Okay, what haven't I answered yet? Okay. There's been a suggestion bandied about that would place the burden of plastic pollution on plastic producers themselves. This, of course, would require monitoring and enforcement of laws that do not exist worldwide. Was this considered by the expert panel because of its challenging feasibility or not? So this type of approach is referred to as extended producer responsibility. And there are some examples of this that are live. The real test case here, though, is going to be in the European Union, which is starting to implement an EPR scheme in the very, very near term. The way that it's probably going to be implemented is, rather than looking at plastic pollution itself, the levies would be placed on the production of plastic in its finished product. And so you'd be essentially implementing the cost at the loading dock rather than trying to go around and collect. And so there's lots of different ways that this could be done. For publicly traded companies, obviously, they need to report to their shareholders about the amount and quantities of things that they're producing. But a lot of these things could be rolled into existing regulatory schemes. The devil, of course, is going to be in the details. And as I said, I think we're going to be learning a lot from what's happening in the EU few years for EPR schemes. But it is fairly commonly proposed as a way to ensure a circular economy. And there's a lot of work which suggests that it is a very, very effective. Okay, another question. How do we think about substitution of plastic with paper from a greenhouse gas perspective? Does this have a higher or lower carbon footprint? All right, so that's not the easiest question to answer, largely because it depends on what happens to the transportation sector. One of the reasons that plastic was broadly adopted by some companies 15, 20 years ago was because of a climate change consideration, because plastic is typically lighter than substitutes. Like a plastic bottle is lighter than a glass bottle. Plastic wrap is lighter than paper. And so as long as we have fossil fueled transportation systems, I have to look at the specific numbers, but I think it's better actually net to continue to use plastic. The issue, of course, is that we know, or at least policies are pushing us in the direction of electrifying our transportation system. And so, for example, in the EU, in many countries in the EU, you will not be able to buy internal combustion engine vehicles in a decade. And so once the transportation system is electrified, then the greenhouse gas calculation changes, whether that be for paper or for glass. And so it's really a question of what's the local context. what's the specific product at this point, and then of course what do we assume into the future about the electricity grid and the sources for fuel in the transportation space. Okay, is there any way to reasonably, actually sustainably clean up the plastics once they end up in the oceans? The simple answer is no. There's been a lot of media and other press about the ocean cleanup, which was founded a number of years ago with the goal of going to the ocean garbage patches and cleaning them up. Turns out it's a really hard engineering problem to go into the middle of the ocean and pick up plastic. Partially because it's a massive engineering problem, but then there's also trade-offs of spending the carbon to build the containers, to run the ships that are out there cleaning it up. And then, of course, because a lot of these systems use some sort of a net, they do interact with the environment themselves. And there's some literature basically stating that the animals that live in the first few centimeters or meter of the ocean would likely be greatly impacted by a lot of these cleanup solutions. And so some of the ecologists working on those systems are pushing back pretty strongly, actually, against scaling this up. The other thing, of course, is that once plastic gets into the ocean, it typically breaks into smaller and smaller and smaller pieces, and a lot of it sinks. So once it's in the sediment, the likelihood of cleaning it up is, I would say, near zero for the vast majority of the ocean. One thing that is different, though, is there's more and more effort, and I think probably useful effort, trying to capture plastics at river mouths. And so there's some examples of that. If you want to see something in action that's got a lot of good press, there's something called Mr. Trash Wheel in Baltimore Harbor, which does, it picks up an impressive amount of plastic in the harbor. And there are other examples of these sort of intercept approaches in rivers. The ocean cleanup is actually doing some of them in rivers as well. And there's other efforts like that are happening around the world. And I suspect those are going to work decently well. The other portion of cleanup that's basically a no-brainer is to do beach cleanups and just pick up plastic when you see it walking down the road. If you can pick it up, obviously it's you can put it in the trash and it can be appropriately dealt with. So I've got time for maybe one or two more. Let me just take a look. Would you say that if you do not see a label on packaging, that it is indeed not recyclable? Would that be a good rule of thumb? I don't think it's a good rule of thumb for a lot of product categories. Obviously, for things like cardboard boxes and paper, that's sort of a no-brainer. It's recyclable in the paper. If you're thinking about things like drink containers, soda bottles, yogurt containers, things that are rigid plastics, it's almost always recyclable. Those are almost all #1 polyethylene, and #1 is recycled almost everywhere in the United States, or at least it's collected for recycling almost everywhere. Where it gets really tricky is sort of in what I would call sort of non-standard products. And again, it really depends where you live. And this is why sort of Googling around to your local waste management system is really important. I know in many cities in the United States, but certainly not all, there is collection for all rigid plastics in a commingled way for plastics 1 through 7. Very few places do plastic bag pickup, although many grocery stores, but again, not all, do centralized plastic bag pickup. So depending on where you live, it could be a good rule of thumb. Certainly, if you're looking at the how to recycle label, if it says, check, in a lot of places, it probably is not recyclable, particularly if you're in a rural area. A comment just came in saying, my understanding is that even very recyclable plastics, number ones and number twos, are only recyclable a few times. Does design for recyclability address this, or am I incorrect? So you are not incorrect. Using current technology, most plastics can only be recycled a couple of times. Design for recycling does address some of these issues. So the sort of limited nature of recycling comes in many products, but again, not all, because of the various additives that go into plastics. So there's no such thing as like a number one plastic, because of all the different additives that are put into polyethylene to give it different material properties. And then of course there's the things like dyes. And so there's some policy push in different places to limit the number of additives, to limit the number of dyes, that would increase the quality of the recycled output, which would allow it to be recycled more times, using traditional mechanical recycling processes. I don't think we're ever going to get to the point where it's infinitely recyclable. Theoretically, chemical recycling, which is basically breaking the plastic down from a long chain polymer into monomers, is indefinitely recyclable if they can figure out a way to make it scale and the economics work. But design for recycling does make plastic more recyclable, yes. All right, I'll do one more. Good one. Okay, there are lots of applications that require single-use plastic. So for those applications, would developing bio-based and biodegradable plastic be a solution? So potentially, and you're right, there are a lot of applications that do require single-use plastic. You know, medical applications are the first thing that come to my mind. You know, you're probably not going to want to use, you know, IV bags more than once. So for those applications, it's really a question of a few things, I think. One is going to be prioritize the investments for in the material science to address the biggest components of plastic waste first. So you know, you're probably not going to want to start with something that's just a small sliver of single-use plastic that does have to remain single-use plastic. So figuring out what those things are is going to be a starting point. The question about bio-based and biodegradable plastics is different, right? So bio-based plastics still produces plastics, right? It's just that instead of using hydrocarbons as the initial source of carbon, you're using photosynthesized carbon, essentially, whether it be from corn or another plant. So that helps reduce, for example, emissions and other forms of environmental degradation on the front end, because you're not drilling anymore, but you still end up with a plastic that is, for all intents and purposes, identical to the fossil fuel based plastic that would come out of other approaches. So bio-based plastics in and of themselves are, depending on the carbon source, depending on how the land is used, depending on whether it was used for food production or other things, or if it's being converted for bioplastics, may or may not, in many cases, probably not a good idea. Biodegradable plastic is another tough question. There are already some biodegradable plastics. If you have, for example, commercial composting facilities, PLA plastic is commonly what you use in the large bins that the company will come by and pick up. And that plastic under industrial composting environments, so temperature and humidity and whatnot, will break down over time. And there is a fair amount of research into the compostable plastic space. The real issue, and where this becomes challenging, is in making sure that it's composted appropriately. Because in most cases, if you try to compost PLA in your backyard, it's just going to sit there because your backyard compost heap doesn't get hot enough. And so the environment just isn't right. So if companies could truly figure out how to make plastic biodegradable in the environment, then you probably have a decent solution in some places. It's going to obviously depend on what other things need to go into the plastic in order to give them the desired material properties, but also sort of where the environment in which the biodegradable plastic is going to be biodegrading, and then the components, like what does it turn into, right? So definitely maybe, I guess, is the simple answer there. So with that, Beth, I will stop talking, and I suspect you have a few things you wanted to say on closeout.
Yeah, you probably can't hear me, but thank you, Jim, for presenting. And we'll officially conclude the webinar for today.